Welcome viewers once again to the lecture series on integral equation under the NPTEL courses. In the last lecture we was discussing about the eigenvalues and eigenfunctions of a Sturm-Liouville boundary value problem. We have established certain property, and one of the important properties was if ymx and ynx, these are two eigenfunctions of a Sturm-Liouville boundary value problem corresponding to two distinct eigenvalues lambda m and lambda n respectively, then we can prove that these two eigenfunctions are orthogonal to each other, and where the orthogonality property we have defined in terms of the integral of these two functions taken with the weight function r x integrated from a to b dx. If this is equal to 0, then we can say these two functions are orthogonal to each other. Now, in this lecture I am going to start with the proof of another theorem that is very much interesting, that we are considering the same Sturm-Liouville boundary value problem ddx of p x dy dx plus q x plus lambda r x y x. This is equal to 0 with the specified boundary conditions and a less than equal to x less than equal to b. So, we are considering this thing. Now, apart from the continuity property of p dot x, q x and r x over the interval a comma b, here we are assuming that r x is either positive on closed interval a comma b or is negative on the closed interval a comma b. And if this happens, that means r x maintain the same sign over the closed interval a comma b, it does not possesses any 0 within this closed interval a comma b, then eigenvalues are real. So, first of all we are going to prove this result, that whenever r x maintains the same sign over the closed interval a comma b, then these eigenvalues are real. So, for the time being we are assuming lambda equal to alpha plus I beta be a complex eigenvalue for this boundary value problem, and we are assuming the corresponding eigenfunction y lambda x, this is defined by y alpha x plus I y beta x. So, where alpha and beta, these are two real numbers, and the eigenfunction y lambda x corresponding to lambda equal to alpha plus I beta can be separated into real and imaginary parts. So, now our target is using the property that r x maintain the same sign over the interval a to b, we are going to prove that beta is identically equal to 0. So, now this y alpha x plus I y beta x is the eigen function corresponding to the eigenvalue lambda equal to alpha plus I beta for this Sturm-Liouville problem. So, therefore, it satisfies the given equation. So, substituting into the given equation, we can write ddx of p x, then y alpha dot x plus I y beta dot x, this entire expression ddx of this one plus q x multiplied by y alpha x plus I y beta x. Then for lambda we have to substitute alpha plus I beta, these multiplied with r x, and then y alpha x plus I y beta x, this is equal to 0. this satisfies the given equation. Now, separating the real and imaginary parts, we can write this can be actually divided into two parts, that is dd x of p x y dot alpha x and plus I dd x of p x times y dot beta x. So, separating real and imaginary parts, we can find that p x this with y alpha dot x, this expression with ddx. So, this is the contribution from the first term, then plus qx y alpha x, and from the rest of the part we can find rx multiplied by alpha times y alpha x minus beta times y beta x, this is equal to 0. And for further calculations, we can rearrange this term into the form, that is dd x of p x y dot alpha x, this one plus q x plus alpha r x, actually we are collecting the coefficient of y alpha x, this times y alpha x minus beta r x y beta x, this is equal to 0. So, this is the expression we are getting from real part. Next, collecting the imaginary part, we can find similarly dd x of p x, this multiplied with y beta dot x, and similarly collecting the coefficient of y beta x, we can find q x plus alpha r x times y beta x plus beta r x into y alpha x, this is equal to 0. So, previous expression was this one, and here we can find this beta y r x y alpha x, this is the two expressions. So, now we can eliminate this q x plus alpha r x, this term from both the equations. So, that means we are multiplying first equation by y alpha x y beta x and second one by y alpha x, and then subtracting, we can find that y alpha x, this multiplied with dd x of p x y beta dot x, this one minus y beta x times dd x of p x y alpha dot x, this expression. Now, this will be equal to minus beta r x, this into y alpha x whole square plus y beta x whole square, this is the expression. And now, you can recall the left hand side is nothing but dd x of p x times Wronskian of y alpha x comma y beta x, this one is equal to minus beta times r x with y alpha square x plus y beta square x. Now, integrating both the sides from the limit a to b, we can find that p x Wronskian of y alpha x y beta x, this one from the limit a to b, this is equal to minus beta integral A to B R x multiplied with y alpha square x plus y beta square x this dx. Now, the left hand part can be considered as that y alpha is an eigenfunction corresponding to the eigenvalue alpha and y beta is the eigenfunction corresponding to the eigenvalue beta. So, therefore, using the previous property what we have discussed earlier, this left hand side is identically equal to 0 and once this is equal to 0. So, therefore, we can write that beta times integral a to b r x multiplied with y alpha square x plus y beta square x this dx, this is equal to 0. Now, we have assumed that r x maintain the same sign over the interval a to b. So, whenever this r x maintain the same sign over the interval a to b, so that means without any loss of generality if we assume r x is positive. So, therefore, integrand r x into y alpha x whole square plus y beta x whole square, this integrand is positive and therefore, there is no chance that integral a to b r x times y alpha square x plus y beta square x equal to 0. So, we are left with the only one option, that is beta equal to 0. So, therefore, whenever this r x maintain the same sign over the interval a to b, then eigen values are real and therefore, associated eigen functions those are also real, and with this we can complete the all necessary proofs for the requirement that a function can be expressed in terms of a collection of orthogonal functions. Now, before going to that discussion, I like to mention one more result that I am not going to prove, that for this kind of Sturm-Liouville boundary value problem, you will be having an infinite sequence of eigenvalues. So, that means, if lambda 1, lambda 2, lambda 3, these are the eigenvalues of a Sturm-Liouville boundary value problem with lambda n and up to infinity. So, then a ordering can be arranged in this particular format, that is lambda 1, this is less than lambda 2, less than lambda 3, less than dot dot, this will be less than lambda n, less than this, with the property limit n tends to infinity lambda n, this is equal to infinity. So, I am not going to prove this result, it is quite tedious. So, we can omit this one, and before going to the orthogonal or orthonormal series expansion of a function f x which is square integrable, I just like to discuss one more thing, that is the orthogonal eigenfunctions we have already defined. Now, what is the concept of orthonormal eigenfunctions? So, we have already familiar with the concept that if a to b r x y m x y n x dx, this is equal to 0 with m not equal to n, then these two functions y m x and y n x, they are orthogonal to each other. Now, clearly you can understand that if r x maintains the same sign and when eigenvalues are real, then for m equal to n, this integral is not equal to 0. So, in that case we can use a normalizing factor such that these orthogonal eigenfunctions can be converted into orthonormal eigenfunctions. So, the concept is that the norm of the eigenfunction, this is defined by actually denoted by norm of y n x, and it can be obtained as this y n norm of square is equal to integral a to b r x y n square x dx. Now, if we define this y n x, so each y n x by its associated norm, so then we can find the family of orthonormal functions, and here I am denoting this as psi n x, and psi nx is nothing but y nx divided by norm of y nx. And with this definition that psi nx equal to y nx by norm of y nx, where each y nx are the eigen functions of a associated Sturm Liouville boundary value problem, you can easily verify that norm of psi n x this whole square, this is equal to 1. So, this result you can easily obtain. Now, before proceeding further, I like to discuss one problem where you can see what are the eigen functions, what is the collection of orthogonal eigen functions and corresponding orthonormal functions, and in a particular manner I am going to consider the example where you can understand what is the utility of R x that is needed to define the orthogonality property and other relevant things, that is for also norm of the function and its role to understand what is the concept of orthonormal eigen functions. So, for this problem I am considering here the equation d d x of x dy dx this plus lambda by x y x, this is equal to 0 with the boundary conditions y dot 1 equal to 0 equal to y dot e to the power 2 pi. Now, you can recall this is a Cauchy-Euler type second order ordinary differential equation. So, in order to solve this problem easily, we can use the change of independent variable x. So, if we use the transformation of variable, that is ln x equal to t. So, then this equation given ordinary differential equation will be converted into d2y dt2 plus lambda, you have to keep in mind this is now yt, this is equal to 0, and associated boundary conditions will be converted into y dot 0, this is equal to 0 equal to y dot 2 pi, because here x equal to e to the power 2 t. So, at the limit x equal to 1 t is 0 and at the limit x equal to e to the power 2 pi, this is t equal to 2 pi. So, this is the boundary conditions. Now, for this problem you can easily verify for lambda equal to 0 and for lambda less than 0, this boundary value problem does not possesses any non-trivial solution. So, non-trivial solution exists whenever lambda greater than 0, and in that case solutions are given by y t, this is equal to C 1 sine root over lambda t plus C 2 cosine root over lambda t. Differentiating we can find y dot t, that is equal to root over lambda C 1 cosine root over lambda t minus C 2 sine root over lambda t. Now, using the condition that is y dot 0 equal to 0, we can find 0 equal to root over lambda times C 1, and already we have assumed lambda greater than 0. So, this implies C 1 this is equal to 0. Then using the right hand boundary conditions, we can find 0 this is equal to minus root over lambda C 2 sine root over lambda times 2 pi. So, lambda greater than 0, we are looking for non-trivial solution. So, therefore, C 2 not equal to 0. So, therefore, we are left with only one possibility, that is sine root over lambda 2 pi, this is equal to 0, and finding its general solution we can find that root over lambda times 2 pi, that is equal to n pi, where n equal to 0 plus minus 1 plus minus 2 and so on, and ultimately we can get the result, that is lambda n, this is given by n square divided by 4, and therefore, n we have to take actually 1, 2, 3 and so on. So, this step we are writing root over lambda 2 pi equal to n pi. This is for as a general solution of the trigonometric equation. Now, for the eigenvalue eigenfunction problem, lambda n is comes down to n square by 4, and therefore, the corresponding eigenfunctions is actually we are having C1 equal to 0, C2 not equal to 0. So, we will be having only cosine terms. So, therefore, resulting eigenfunctions are y n x, this is equal to C n cosine n by 2 ln x. This is actually eigenfunctions, and eigenvalues are given by lambda n equal to n square by 4, where n equal to 1, 2, 3 and so on. Now, we are actually interested to find out the corresponding orthonormal eigenfunctions. So, these are orthogonal eigenfunctions, and here you can verify without this additive this multiplicative constant C n, that y m x, y n x with r x, this is required, then integral x equal to 1 to e to the power 2 pi dx, this is equal to 0 when m not equal to n, and there is no harm if you proceed with this C m and C n, because integral will comes out to be 0. So, whatever may be the finite values of C m and C n, this condition will be satisfied, and therefore, this norm of this particular problem you can calculate easily, that is C n square integral 1 to e to the power 2 pi 1 by x cosine square n by 2 ln x dx. So, now using the change of variables, that is from ln x equal to u, you can easily convert it to the integral C n square integral 0 to 2 pi cosine square n by 2 u du. Here we are substituting ln x, this is equal to u. So, that means the r x part, r x equal to 1 by x, and then 1 by x dx will be your du, and limits will be changed to from 0 to 2 pi. So, this will be equal to C n square by 2 integral 0 to 2 pi 1 plus cosine n u du. So, this will be C n square by 2 u plus sin n u divided by n, this limit from 0 to 2 pi. Now, here you can recall the values of n is equal to 1, 2, 3 and so on. So, there is no contribution from the part sin n u by n, at 0 it is 0 and sin 2 n pi equal to 0, because n is ranging over 1, 2, 3 and so on. So, that means we are left with C n square by 2 times 2 pi. So, this is equal to C n square pi. So, now if we divide this y n x equal to C n cosine n by 2 ln x by C n times root over pi. So, then we will be having the corresponding orthonormal eigenfunctions. These are nothing but 1 by root over pi cosine of n by 2 ln x. So, this particular set, that is psi n x equal to 1 by root over pi cosine n by 2 ln x, where n equal to 1, 2, 3 and dot dot up to infinity. This set psi n x n from 1 to infinity, this is actually a set of orthonormal eigenfunctions for the associated Sturm-Liouville boundary value problem. Now, our target is to find out the orthonormal eigenfunction expansion or whatever may be the orthogonal eigenfunction expansion for a particular problem, this g x. So, that means we are interested to express g x as a summation n runnings from 1 to infinity C n y n x, where the sequence y n x n runnings from 1 to infinity, this is a collection of a family of orthogonal eigenfunctions associated with a Sturm-Liouville boundary value problem. And where this function g x is defined over the interval a comma b, and for the forthcoming discussion that whether this expansion can be obtained or not in order to get the answer and all possible interchange of integral and the infinite summation, we are assuming the property of g x, that is g x is square integrable, that we are actually assuming. I am not going to details of the proof of this results that where this can be done, but it can be found in any book on Fourier series and related analysis. And the property is that in terms of mathematics we can say that when R x, that is the function involved with the Sturm-Liouville boundary value problem, if integral a to b R x g x whole square dx, if this is finite, then we can say this g x is actually square integrable function. So, now we are actually going to derive the coefficients C n such that g x can be expressed as summation n runnings from 1 to infinity C n y n x, and in order to derive the coefficients C n, we will be using the orthogonality property of the eigenfunctions. So, to find out this C n, we can multiply this expression on the both side by R x into y m x. So, therefore, we can write R x y m x g x, this is equal to R x y m x, then sigma n runnings from 1 to infinity C n y n x. Now, integrating both sides from the limit a to b, we can find integral a to b R x y m x g x dx, this is equal to integral a to b R x y m x sigma n equal to 1 to infinity C n y n x dx. Now, using the property that g x is square integrable and other relevant properties of uniform convergence of this series, and then interchanging the integral and summation, we can find this will be equal to sigma n runnings from 1 to infinity C n integral a to b R x multiplied with y m x y n x dx. Now, you can recall that these integrals, integral a to b R x y m x and y n x, since they are taken from collection of orthogonal functions, this is equal to 0 for all m not equal to n, and this quantity is non-zero whenever this m equal to n. So, ultimately we will be having integral a to b R x y m x g x dx, this is equal to C m integral a to b R x y m x the square dx. This is actually C m, the unknown coefficients, and therefore, each unknown coefficients C m can be obtained as integral a to b R x g x y m x dx divided by integral a to b r x y m square x dx. So, this result is valid for m equal to 1, 2, 3 and so on. So, this is the coefficients for Cm. So, in this way if we calculate the coefficient Cm, then we can find the expansion of a function gx in terms of orthogonal eigenfunctions ymx, or it can be said as the Fourier series for the ymx, where this gx, that is gx is square integrable over the closed interval a comma b, that condition is satisfied. And if instead of orthogonal eigenfunctions, if we consider the orthonormal eigenfunctions, then this y m and y n will be replaced throughout by psi m and psi n, and since the norm of psi n, this is equal to 1. So, this expression appearing in the denominator for Cm will be identically equal to 1. So, that means just for your note, if we consider gx is equal to sigma n runnings from 1 to infinity C n psi nx, where psi collection of psi nx, these are actually orthonormal eigenfunctions n runnings from 1 to infinity, then you will be having this coefficients C m, this is equal to integral a to b r x g x psi m x dx only. So, no term will appearing in the denominator. So, this is actually expression for that is orthonormal eigenfunction expansion of a function gx, which is defined over the closed interval a comma b. Now, we are going to apply this concept of expanding a function defined over the closed interval a to b in terms of orthonormal eigenfunctions to construct the Green's function for a non-homogeneous Sturm-Liouville boundary value problem. So, that means our target equation is d d x of p x dy dx, this one, plus q x plus lambda y x equal to g x with the associated boundary condition, say y a equal to 0 equal to y b. Of course, you can use the general separated boundary condition, but for your simplicity I am considering here the simple 0 boundary condition at the both end for y, that is y a equal to 0 and y b equal to 0. And one more important property that you have to notice here, for simplicity I am assuming r x equal to 1. So, without assuming r x equal to 1, same result can be derived, but for simplicity of forthcoming mathematical calculations I am assuming r x equal to 1. This is one thing, and one more thing, here I can denote this L y x, this is equivalent to d d x of p x dy dx, this plus q x y x only. So, this is just a difference in notation for L y x. In the previous lectures you can find that L y actually involves this lambda r x y x terms also. So, with this definition, so if we denote this expression, that is d d x of p x dy dx plus q x y x as L y x, then the given equation can be written as L of y x plus lambda y x, this is equal to g x. Now, in this case y x is the unknown function and g x is a given function. So, we are assuming the expression for y x in terms of orthonormal eigenfunctions can be written as y x equal to summation n runnings from 1 to infinity alpha n psi n x, where alpha n is equal to integral a to b y x psi n x dx. R x will not be coming here because we have assumed R x equal to 1, and then g x, this will be equal to summation n runnings from 1 to infinity beta n psi n x, where beta n is equal to integral a to b g x psi n x dx. And one more property, that psi n x, they satisfies this relation, that is L of psi n x, that is equal to minus lambda n psi n x, because this psi n x, they are actually eigen functions corresponding to the eigenvalues lambda n of the given problem. Now, if we substitute these two expressions y and g into the given equation, then we can find that L of sigma n runnings from 1 to infinity alpha n psi n x plus lambda integral summation n runnings from 1 to infinity alpha n psi n x, that is equal to sigma n runnings from 1 to infinity beta n psi n x, and here we can write this is equal to sigma n runnings from 1 to infinity alpha n L of psi n x plus lambda sigma n runnings from 1 to infinity alpha n psi n x, this is equal to summation n runnings from 1 to infinity beta n psi n x, and here we can use this result, that is L of psi n x equal to minus lambda n psi n here for each term at this particular position. So, using this result we can write this will be equal to minus summation n runnings from 1 to infinity alpha n lambda n psi n x plus lambda sigma n runnings from 1 to infinity alpha n psi n x, this is equal to sigma n runnings from 1 to infinity beta n psi n x, and at the next step we can write this implies sigma n runnings from 1 to infinity, this will be alpha n times lambda minus lambda n psi n x, this is equal to sigma n runnings from 1 to infinity beta n psi n x, and at the next step we can write sigma n runnings from 1 to infinity this alpha n multiplied with lambda minus lambda n minus beta n psi n x, this is equal to 0. Now, this is an expressions of the form you can try to understand that C 1 psi 1 x plus C 2 psi 2 x plus C 3 psi n x plus dot dot up to infinity, that is equal to 0, and we can easily prove that if this happens then every coefficients of psi n x will be identically equal to 0, because the family of orthonormal eigenfunctions, they are set of linearly independent functions. So, using the set of linearly independent property, or you can apply the orthogonality property in order to derive all these coefficients are exactly equal to 0. So, from here we can write that alpha n, this is equal to beta n divided by lambda minus lambda n. So, this is the derivation of alpha n equal to beta n by lambda minus lambda n. Now, at this was actually our main goal, because for the given problem y x is unknown, g x is a given function. So, once we are able to solve the eigenvalue eigenfunction problem associated with the given Sturm-Liouville boundary value problem. So, immediately you will be having lambda n's, these are known, psi n x, those are also known, and once you know the lambda n and psi n. So, using the known function you can find out beta n, because beta n are the coefficients involved in the orthonormal eigenfunction expansion for g x. So, therefore, beta n is known. So, from this relation you can clearly understand that lambda is a parameter, beta n are known, lambda n are known. So, each unknown quantity alpha n which are actually involved with the unknown function y x is now determined. So, therefore, using the definition of y x we can write y x, this is equal to sigma n running from 1 to infinity alpha n psi n x. So, this is equal to sigma n running from 1 to infinity beta n divided by lambda minus lambda n psi n x, and here we can recall the definition for beta n. So, therefore, this is equal to sigma n running from 1 to infinity psi n x divided by lambda minus lambda n integral a to b. This beta n is nothing but g s psi n s d s, because x is already involved here. So, we are writing this definition for b n in terms of the variable s, and then interchanging the summation and integral sign, that is allowed with the assumption that g x is square integrable. We can write this is equal to integral a to b, integral a to b g x, then sigma n running from 1 to infinity psi n x psi n s divided by lambda minus lambda n this d s. And if we write this expression as equal to minus integral a to b g s capital G x comma s d s, then G x comma s, this is equal to minus sigma n running from 1 to infinity psi n x psi n s divided by lambda minus lambda n. So, this is equal to simply sigma n running from 1 to infinity psi n x psi n s divided by lambda n minus lambda. So, this is the way by which for a given Sturm-Liouville boundary value problem, if we are able to find out the family of orthonormal eigenfunctions and associated eigenvalues lambda n, then Green's function can be also expressed as a series of orthonormal eigenfunctions. So, that means, this is actually the expression for Green's function in terms of orthonormal eigenfunctions. So, you can say this formula is involved with the orthonormal eigenfunction expansion of a Green's function associated with a Sturm-Liouville boundary value problem. Now, we consider a specific example. So, this example is that we are considering this given equation d2y dx2 plus lambda y, this is equal to g x, which is defined over the interval x less than equal to 0 less than equal to pi. This is the interval, and where the given boundary condition y 0, this is equal to 0 equal to y pi. So, first of all we have to find out the eigen values and eigen function for the associated homogeneous problem. So, our target problem is d2y dx2 plus lambda y, this is equal to 0 with associated boundary conditions y0 equal to 0 equal to y pi. If you proceed in an usual manner, you can find the eigen functions y n x, this will be C n sin n x, and eigen values lambda n, these are given by n square, where n equal to 1, 2, 3 and so on. So, with this definition of y n x, if we calculate the norm of this function y n and divide it by its norm, so then we can obtain the corresponding family of orthonormal eigen functions y n x, this is equal to root over 2 by pi sin of n x, where n equal to 1, 2, 3 and so on. And just for your verification, you can check that here the given problem is d2y dx2 plus lambda y equal to 0. So, if you compare with the standard format of the Sturm-Liouville boundary value problem, so r x equal to 1, that is positive, which is positive throughout the interval 0 to pi, and therefore, all the eigen values are real, each eigen values are real, and further these eigen values lambda n equal to n square for n equal to 1, 2, 3 and so on. So, therefore, you can easily verify that the ordering that I have mentioned earlier, it also satisfying also the increasing order, that is lambda 1 is less than lambda 2, less than lambda 3 and so on, and easily you can verify limit n tends to infinity lambda n, that is also equal to infinity. And then using the normalization condition, you can find out the family of orthonormal eigen functions psi n x equal to this one, and therefore, using the formula just we have derived, that is g x comma s is equal to sigma n runnings from 1 to infinity psi n x psi n s divided by lambda n minus lambda. So, we can write for this problem Green's function g x comma s is nothing but 2 by pi summation n runnings from 1 to infinity sin n x sin n s divided by n square minus lambda. This will be n square, not lambda square. This will be n square minus lambda. So, this is the Green's function for the given problem, and then solution to the given problem y x, this will be equal to 2 by pi sigma n runnings from 1 to infinity sin n x divided by lambda minus n square integral 0 to pi g s sin n s ds. Here this 1 by n square minus lambda, this is changed to 1 by lambda minus n square, because the solution y x is equal to minus integral a to b, here a equal to 0, b equal to pi, minus integral a to b g s, then capital G x comma s ds. So, that minus sign will be absorbed here. So, results in y x equal to 2 by pi integral n runnings from 1 to infinity sin n x divided by lambda minus n square integral 0 to pi g s sin n s ds. So, of course, with some known g s, you can evaluate this integrals, that what will be the result for integral 0 to pi g s sin n s ds. So, this is actually the solution of the Sturm-Liouville boundary value problem in terms of orthonormal eigenfunctions, and if you try to understand that this y x will be solution of the associated Fredholm integral equation, that means if the given ordinary differential equation is converted into a Fredholm linear integral equation, then this expression is also a solution to the given problem. Now, these are the necessary results what will be required to discuss further the Fredholm alternative and Hilbert-Smith theory associated with Fredholm integral equation. So, these are all necessary tools in order to find out the solutions of the Fredholm integral equation. So, today this lecture I can stop at here. In forthcoming lectures, I will be considering similar approach what we have adopted for the Volterra integral equation. Some of them can be applied in order to find out solution of the Fredholm integral equation, and then we will be considering the Fredholm 3 theorem, first theorem, second theorem, third theorem, and then Hilbert-Smith theory to obtain the solutions for Fredholm integral equations. So, thank you for your attention.